Imagine a multi-million-dollar factory floor. You've got this piece of heavy machinery. It's about the size of a city bus, and it's cutting aerospace-grade aluminum.
Right, just a massive, incredibly complex system.
Exactly. It's this absolute symphony of modern engineering. But then, almost imperceptibly at first, the surface finish on the metal just turns rough.
Yeah, that's the first sign.
And then the machine starts to scream, like this horrible, high-pitched vibration. Production completely halts. Those critical delivery deadlines you had, blown out of the water.
Which is terrifying for any plant manager, honestly.
Oh, absolutely. And the crazy part, the culprit behind this catastrophic, literally six-figure breakdown, is just a microscopic patch of rust caused by a single drop of damp air.
It sounds impossible, right? But it happens all the time.
Welcome to this deep dive. Today, our mission is to explore what is basically the ultimate real-world example of the butterfly effect in precision manufacturing.
Yeah, we're drawing from this highly specialized industrial maintenance guide, specifically focused on aluminum profile machining centers.
And we're bringing you along for the ride. Because even if you aren't running a CNC machine shop, and I'm guessing most of you listening probably aren't, this is just an absolute masterclass in how tiny, overlooked frictions can completely derail high-performance systems.
It really is a fascinating journey because, it completely subverts our intuition about heavy industry.
Right.
We naturally assume it takes these massive dramatic forces to bring down tons of solid steel. We don't expect a cosmetic annoyance like something you might casually scrub off a garden trowel to be the fatal blow.
Exactly. A seemingly harmless spot of moisture on Monday literally translates to a dead production line and idle workers by Friday. So, okay, let's unpack this.
Let's do it.
Because to understand why a tiny patch of rust is a literal machine killer, we first have to understand the absolute extreme environment these machines operate in. We are talking about machining aluminum, and the guide makes it very clear that aluminum is, well, it's a very specific beast.
It really is. It's highly ductile, which means, essentially, aluminum is fundamentally a soft, pliable metal. Right. And in these modern machining centers, operators are cutting it at blistering speeds.
How fast are we actually talking here?
Well, the spindles, those are the massive rotating steel shafts that actually grip and drive the cutting tools they're spinning at 15,000 revolutions per minute, sometimes even faster.
Wow. 15,000 RPM.
Yeah. The cutting edge itself is traveling through the metal at up to 1,500 meters per minute.
Which is just a staggering amount of kinetic energy. But I want to pause on the material itself for a second.
Sure.
Because if we were cutting a hard metal, like steel, at a slower speed, it seems like we wouldn't have this specific crisis. The guide kind of made me think of it like this: cutting soft aluminum at 15,000 RPM is less like chopping wood and more like spreading warm butter on hot toast.
That's a great analogy, actually.
Right. The metal actually wants to smear. It essentially friction welds itself to the cutting tool, acting literally like a kind of glue.
Yeah, and that is the exact mechanism that creates the perfect storm here, because you have these sticky, soft aluminum chips just flying everywhere.
Oh, I can imagine.
And simultaneously, the machine is blasting high-pressure liquid coolant directly into the cutting zone.
Because of the heat, right.
Exactly, to manage that intense friction heat. But those sticky aluminum chips, they adhere to the steel spindle, and they act like little sponges.
Oh, no.
Yeah, they trap that wet coolant directly against the bare metal of the machine.
So the machine is basically wrapping itself in a wet blanket while spinning at 15,000 RPM.
Pretty much, yeah.
But let me push back on the physics of this for a second. If this heavy machinery is built to handle thousands of pounds of cutting force, why does the speed make this trapped moisture so instantly fatal?
Well, what's fascinating here is how the extreme speed radically changes the physical requirements of the machine.
Okay, how so?
At 15,000 RPM, these spindles require an incredibly strict dynamic balance. They're calibrated to a standard known as a G0.4 grade.
G0.4. That sounds like an incredibly tight tolerance.
It is. It's exceptionally tight.
Because if I'm visualizing the physics right, at 15,000 RPM, even a fraction of a millimeter of imbalance must generate like a massive amount of centrifugal force. Are we talking enough force to physically bend the steel?
It creates this violent lateral whipping motion. The tolerance for any wobble at G0.4 is virtually zero
Wow.
because vibration scales exponentially with speed, right?
Mm.
So a single microscopic rusted spot or even just a tiny clump of sticky aluminum trapping a water droplet throws the entire rotational mass off its perfect center.
So the extreme speed doesn't just make the rust happen faster by, drawing in coolant mist.
Right.
It makes the physical consequence of the rust immediately destructive to the machine's geometry.
Exactly. You've got it.
Here's where it gets really interesting for me, though, because we're moving from the macro environment, this wet, sticky, high-speed workshop, down to the microscopic level.
Yeah, this is where the real damage happens.
Right, and the source material explains exactly how this rust destroys the mechanics of the machine, and it all hinges on the physical connection between the spindle taper and the tool holder.
Yeah, to picture this, you really have to understand that a spindle taper is a highly precise conical hole.
Okay.
The cutting tool slides into this cone, and in a healthy machine, the metal of the cone and the metal of the tool holder meet in a flawless, flush, metal-to-metal fit.
So no gaps at all.
None. There's no air between them. They essentially become one solid piece of steel.
But then the rust eats away at that flawless surface.
Right, it creates these microscopic gaps and pits in the steel.
And to picture why a microscopic gap is catastrophic, I was thinking about this. Imagine running an Olympic sprint in shoes that are just like half a size too big.
Yeah, I like that.
Yeah, like you've trained perfectly, your muscles are firing, your lungs are clear, but because of that tiny microscopic wiggle room inside your shoe, your entire form is just ruined.
Yeah, you lose the power transfer to the ground.
Exactly, and you stumble. And in the machining world, that tiny microscopic wiggle has a name, right? It's called radial runout.
Radial runout is the absolute nightmare scenario for a machinist
I bet.
because it means the tip of the cutting tool is no longer spinning in a perfect concentric circle. It is spinning slightly off-center.
And at those speeds.
Right. When a cutting tool is whipping around off-center at 1,500 meters per minute, it destroys your machining precision entirely.
So the tool is physically wobbling?
Yes, it's slamming into the aluminum unevenly, and the surface finish of the metal comes out rough, covered in what the industry calls chatter marks.
Chatter marks.
Yeah, from the severe vibration.
But wait, let me play devil's advocate here. If we are just talking about rough metal and a little vibration, I mean, I have surface rust on the undercarriage of my car right now.
Sure, most people do.
Right. And I hit a pothole, the car vibrates, but the engine keeps running fine for another 100,000 miles. Why does this microscopic loss of rigidity in the spindle lead to the complete death of the tool?
Well, it comes down to a paradox in how the machine manages the extreme heat of the cutting process.
Okay.
In your car, the rust is on a passive surface.
Yeah.
But the spindle taper is an active thermal pathway. And this brings us to the most insidious effect of the rust, which is thermal insulation.
Yes. This is the massive aha moment from the guide. The rust isn't just a physical scratch. It acts as a literal thermal blanket.
Precisely. Rust does not conduct heat well at all.
Wow.
And when you are carving solid metal at those speeds, the cutting edge generates a staggering amount of thermal energy.
Right.
Normally, that flawless metal-to-metal fit we talked about allows all that intense heat to transfer out of the small cutting tool, flow up into the massive steel body of the spindle, and safely dissipate.
So the spindle basically acts as a giant heat sink.
Exactly.
But the microscopic layer of rust blocks that heat transfer. It literally traps the heat down in the tool holder, so the machine can no longer sweat or, cool itself down.
Right, the tool essentially cooks itself from the inside out.
That is wild.
Because the heat has nowhere to go, the temperature of the cutting tool spikes wildly. And this leads to rapid material fatigue in the metal of the tool itself.
It means it breaks faster.
Much faster. The guide specifically notes that this thermal trapping can cut the lifespan of your expensive carbide cutting tools entirely in half.
Half. That's a huge cost. And the sources mention an even worse scenario that stems directly from this trap heat.
Oh yeah, it gets worse.
Because the rust mixes with the wet liquid coolant and the fine sticky aluminum dust that's floating around in the cut.
Yeah.
And because it's baking at such a high temperature, it forms this hard corrosive glue. So now, not only is your tool vibrating wildly and overheating, but it actually gets permanently friction welded inside the spindle.
Which is just a disaster.
You literally can't get the tool out of the machine to change it.
And that perfectly illustrates how the micro-destruction of the tool rapidly escalates into the macro-destruction of the entire multi-million-dollar machine.
Right. The damage refuses to stay isolated.
Exactly. The guide actually refers to the spindle as the heart of the CNC machine. If the heart starts pumping poison, well, the entire body begins to shut down.
And that poison is the rust itself.
Yep.
Because as the rust eats into the steel taper, it causes deep metal fatigue, the surface integrity weakens, and the vibration literally shakes the rust loose.
Yeah, it flakes right off.
Right. So now you have abrasive rust dust, which is essentially like dumping sand floating around inside an internal environment that is supposed to be clinically, surgically clean. Where does that dust go? Right up into the precision spindle bearings.
And the bearings are the absolute unsung heroes of this entire operation.
Oh, totally.
They are what allow a massive steel shaft to rotate smoothly at 15,000 RPM without tearing itself apart.
So when you get rust dust in there...
When you introduce abrasive rust dust into those bearings, you drastically increase the internal friction.
Right.
And increased friction generates even more heat, burning away the bearing grease. Suddenly, those highly engineered bearings are wearing out at a fraction of their normal lifespan.
Which forces the human element to get involved, because the operators running the machine aren't blind to this cascade of failures.
Yeah, they definitely notice.
They hear the terrible screaming noise the machine is making that chatter. They see the ruined surface finish on the aluminum part, so they react, and their natural instinct is to dial the machine back.
Which makes sense on a human level.
Yeah, they reduce the cutting speeds to try and smooth out the vibration and quiet the noise down.
But if we connect this to the bigger picture, that instinctive human reaction is where the mechanical failure transforms into a severe business crisis.
Yes.
Because in modern manufacturing, everything is timed to the second.
Completely. Because slower cutting speeds mean longer cycle times, you are suddenly making far fewer parts per hour.
Your factory's throughput just plummets.
It perfectly illustrates the lean manufacturing nightmare. We went from a microscopic invisible layer of moisture to a bad surface finish to literally starving the entire downstream assembly line because the machine can't output parts fast enough.
It's a silent drain on company profits, disguised as a minor cosmetic issue.
Wow, yeah.
You are losing money on every single slower cut. And the real tragedy is slowing the machine down doesn't actually stop the degradation.
It just hides it.
Exactly. It just masks the noise while the corrosion spreads deeper into the internal anatomy of the machine.
So it hits the drawbar next, right?
Yes. The drawbar is this powerful internal mechanism running down the center of the spindle that physically pulls and locks the tool into place.
Okay.
If the corrosion reaches the drawbar, the clamping mechanism sticks. Automated tool changes start to fail.
Huh.
And from there, the rust reaches the internal pneumatic and hydraulic seals.
Oh, man.
Yeah, it causes the rubber and polymer materials to break down entirely.
And that is the final domino falling. The seals fail, the pressure drops, and the spindle freezes or just breaks completely.
It's game over for that machine.
Right. No, you weren't just running slowly, you were dead in the water. You were facing an incredibly expensive, highly specialized spindle rebuild that can take weeks.
Weeks of downtime.
You are blowing past your customer delivery dates. And perhaps the most painful part for any business owner, you are paying an entire shift of workers just to stand around on the factory floor and wait for a machine that is completely frozen.
It's brutal.
The hidden costs of ignoring that little orange tint on Monday are absolutely staggering by Friday.
Which, shifts our focus to the operational reality.
Right. How do we fix it?
Since we know that high speeds and high pressure liquid coolants are non-negotiable, they are the fundamental requirements to cut aluminum efficiently.
Right. You can't just turn off the coolant.
Exactly. And since we know that rust is a guaranteed machine killer in this wet environment, operators are essentially fighting a daily war against physics.
So how do they actually win?
Well, that brings us to what the guide calls the proactive playbook. We move from the anatomy of the disaster to the daily operational defense.
Okay, let's hear it.
And the source material lays out a very specific, almost militant regimen. It starts with the air in the room. You have to keep the entire workshop humidity strictly between 40% and 60%.
Wait, 40 to 60%. That is an incredibly narrow window to maintain in a massive, drafty industrial space.
It really is. It requires dedicated environmental control. We're talking industrial dehumidifiers running constantly to pull the ambient water out of the air.
Because if it gets too humid...
Right. If the humidity creeps above 60%, the ambient air reaches a dew point too easily when it contacts the cool steel of an idle machine. It literally condenses into pure water droplets directly inside the spindle.
The guide also points out a hidden trap with the air system itself, which I thought was fascinating.
Oh, the compressed air?
Yes. Factories run on compressed air, and if your compressed air lines are moist, Every time the machine uses an air blast to clear away those sticky aluminum chips, you are literally taking a hose and blasting atomized water straight into the sensitive spindle area.
Yeah, you're just injecting the problem right into the heart of the machine.
So bone dry air is an absolute must. And then you have to manage the chemistry of the coolant. You can't just dump cheap fluid and tap water into the machine.
No, absolutely not. The chemistry is critical because coolant is an emulsion. It's this delicate balance of water, oils, and anti-rust additives.
Right.
The guide stresses that you have to mix it exactly to the manufacturer's ratios. But more importantly, you have to monitor and change it regularly.
Because it goes bad.
Yeah, under the extreme heat and pressure of cutting, the chemical bonds in the anti-rust additives physically break down over time.
Wow.
If you run old coolant, you are essentially just blasting the machine with pure corrosive water.
But the environmental control and the chemical engineering of the coolant are only half the battle. Because the ultimate intervention is the daily human ritual.
This is the big one.
The guide is uncompromising on this. Operators must clean the spindle taper and the tool holders after every single shift. Not once a week, every shift.
And the method of cleaning is just as important as the frequency. They must use perfectly dry, compressed air and lint-free cloths.
Right. The guide explicitly warns against ever using abrasives.
Yeah, no sandpaper, no wire brushes, no matter how stubborn that sticky aluminum chip is.
Because if you take sandpaper to that highly engineered cone, you scratch the steel, you change the shape of the taper, and you've just artificially created the exact same microscopic gaps and radial runout that the rust would have created.
Exactly. You do the damage yourself.
You just skip the rust step and go straight to destroying the machine.
Right. You have to preserve that flawless G0.4 balance fit at all costs.
Okay, so you wipe it down.
Once the taper is meticulously cleaned and perfectly dry, the final step is applying a specialized anti-rust oil.
Like a WD-40 kind of thing.
Better. This isn't just a standard lubricant. This specific oil has a very low surface tension, allowing it to creep into the microscopic pores of the steel.
Oh, nice.
Yeah, it physically displaces any remaining water molecules, creating an impermeable hydrophobic wall against the wet workshop air.
That's brilliant.
Throw on some protective covers to block any splashing coolant while the machine is sitting idle overnight, and you've effectively neutralized the threat.
The guide does offer one concession, though. It says if you see very light surface rust, you can use an approved chemical rust remover immediately to dissolve it.
Right, but you have to be fast.
Yeah. But if the rust has taken hold and the metal is actually pitted, you don't play hero. You call a professional to regrind the spindle before you completely destroy the geometry of the machine.
Yeah, don't try to sand it out yourself.
But looking at this entire playbook, running dehumidifiers, checking fluid chemistry, wiping things down with a dry cloth, and rubbing some hydrophobic oil on the steel. The ultimate solution here isn't some million-dollar, next-generation technological upgrade.
No, not only.
It is just basic, disciplined hygiene, which leads me to challenge the premise of this entire epidemic.
Okay, go for it.
If the fix to saving a spindle that costs tens of thousands of dollars is literally just taking 5 minutes to wipe it down and apply oil at the end of the shift, why is this such a massive, widespread problem? Why do highly trained professional machinists let their expensive equipment rot?
Well, this raises an important question, and it really gets to the heart of human psychology in high-stakes production environments.
Yeah, I guess it does.
Because in a modern factory, the primary metric is always output. The scoreboard only tracks faster cycle times and more parts out the door.
Right. Nobody gets a bonus for having the shiniest spindle.
Exactly. The proactive steps, taking the time to measure coolant ratios perfectly, intentionally stopping a running machine to wipe out a spindle with a lint-free cloth after every single shift that requires a high degree of upfront effort for zero visible reward.
It requires an ironclad culture of discipline.
It really does.
Because taking 5 minutes to dry off a piece of metal at the end of an exhausting 12-hour shift probably feels like an annoying administrative interruption to the real work of making parts.
It feels like you are slowing production down. When the machine is running perfectly fine today, the rust prevention feels like invisible work.
Because the rust itself is invisible right up until the moment it destroys the machine.
Precisely. Human psychology profoundly struggles to weigh the minor, annoying, upfront cost of daily maintenance against the abstract, devastating cost of a reactive repair months down the line.
We naturally prioritize the visible demands of today over the invisible threats of tomorrow.
It's the classic deferred maintenance trap, but accelerated by a 15,000 RPM environment.
Yeah, you don't immediately feel the consequences when you skip checking the airlines on a Tuesday.
Right.
Just like you don't hear the bearings dying the exact moment a water droplet hits the taper.
But the physics of the machine never stop keeping score. The compounding interest on that deferred maintenance is a completely frozen production line.
It really is a phenomenal journey when you step back and look at the causality we've mapped out today.
It really is.
I mean, we started with sticky aluminum chips and high-pressure liquid splashing around. That traps a tiny bit of moisture, which oxidizes the steel and creates microscopic gaps in the taper.
Yep.
Those gaps cause radial runout and massive centrifugal vibrations, which then act as a thermal blanket that prevents the machine from sweating, effectively cooking the tools from the inside out.
A perfect storm.
And then that heat-damaged rust flakes off, gets crushed into the bearings, burns up the grease, freezes the drawbar, and results in a completely dead factory floor with workers standing around waiting for a rebuild.
Wild to trace it all back.
And the entire catastrophic chain reaction is completely preventable through nothing more than strict daily hygiene, wipe it down, keep the air dry, oil it up.
It's a powerful reminder of how deeply interconnected these high-performance systems are.
Oh.
You really cannot separate the microscopic environment from the macroeconomic outcome of the business.
You really can't. Well, we've unpacked the extreme physics, the thermal paradoxes, and the lean manufacturing reality of spindle rust today. But as we wrap up this deep dive into the source material, I want to hand it over to you for one last thought.
Sure.
What should we, as listeners, be taking away from this war against microscopic friction?
Well, I would leave you with this to mull over. We've seen how a microscopic, almost invisible layer of surface moisture can completely bring down a perfectly engineered, heavy-duty precision manufacturing line.
Right.
It makes you wonder, what other invisible frictions or inefficiencies in your own daily life are you ignoring?
Oh, that's a good question.
Right. Whether it's an outdated process in your business, a glitch in your technology, or even just a tiny bad habit in your personal routine. What microscopic compounding rust are you letting slide today simply because it seems too small to matter right now?